So the question was, which lone pair in this molecule is the most nucleophilic? So in terms of condensing with an aldehyde or a ketone. So a nitrogen next to a carbonyl, that is an amide. An amide nitrogen is not nucleophilic due to resonance. So in this molecule, you have two types of amides. Overall, that central carbon is at oxidation state 4. So if we cover up this nitrogen here, that functional group is called a urea. So a urea is like two amides. So amide, amide. They just happen to be next to each other. So those lone pairs are delocalized into the carbonyl through resonance. So the other nitrogen, that nitrogen resembles a primary amine. So that's going to be the one that will condense. So if it condensed with any sort of carbonyl, it would form an imine.
And that one's further?
Yeah, so if we draw one of the resonance forms, just so you can see it. So the other amide will do this as well. This lone pair will delocalize. Onto the carbonyl oxygen. So, I mean, if you're making the connection of what's happening there, the lone pair is not on that nitrogen, it's on the oxygen. So, someone asked a question about like rates. If you were using that as a nucleophilic component in a condensation reaction with an oxidation state 3 functional group. So given these oxidation state 3 functional groups in that starting amine compound, which one will react the fastest with the amine? So given the starting nitrogen compound, which one of the oxidation state 3 choices there, A, B, C, or D, will react the fastest with that amine? So again, as a review, here are the oxidation state 3 functional groups. Ester, acid chloride, anhydride, and amide. So the rate, in terms of the trend, B is greater than C, is greater than A, is much, much greater than D. So that would be the trend. And that's related to the leaving group ability of X. And X is would be the ethoxide, the chloride, the carboxylate, or the amide that ends up leaving.
So why is the anhydride greater than the ester?
So those are the leaving groups. If you consider the conjugate acids. Trying to be mindful of my G's because apparently there's an issue with reading them. So those are the conjugate acids. That's pretty straightforward at this point. And then you're making the association between that and the pKa. So the alcohol is 15. We'll just call the acid -5, carboxylic acid 5, and then we'll call the amide or the amine, say 40. Now, if we stick those numbers back above the letters in the trend, what do we have? We have -5. Then we have 5, then 15, then 40. So there you can see it's based on the pKa. So the strongest acid has the weakest conjugate base. And so what that means is it's the most stabilized leaving group. This is the least stabilized. That's not happy. It's very reactive. So in terms of leaving groups, this is the most reactive, this is the least reactive. So there's different ways or dimensions to think about that.
So D is the least nucleophilic, but the most reactive, is what you're saying.
In terms of the leaving groups, yes.
So you were asking like which substrate A through D would react best with the amine, or what was the question for that?
Which one of these will react the fastest with this?
Okay, fast. And so like, if we know that table of trends that you gave us, like that should be an easy question.
Yeah, I mean, this is,
Same table.
like, if you know, like, these functional group names, I mean, and understand what the substructure is of an ester, the only stuff that changes is like what's here and what's there. So, I mean, that's really,
This is the basics to like,
Yeah.
and stuff's gonna be attached depending on the
Correct.
difference.
That was supposed to be my next question, and if like we add on, it still doesn't matter, because we're just looking at like that part of the structure.
right.
Okay.
Next question?
Bioavailability oxidation.
Yeah. So Baeyer-Villiger oxidation is when you're taking an oxidation state 2 functional group and treating it with a peroxy acid. So peroxy means there's a peroxide, that's an OO sigma bond. So we're using MCPBA, which is metachloroperoxybenzoic acid. So we're using a ketone, and the ketone has alpha and alpha prime. Methylene groups there. So a ketone is going to form what? What functional group? Just in general. So it's going to form an ester. So there's the association you want to make. A ketone forms an ester, and an aldehyde forms what? Carboxylic acid.
And you can do both in this type of problem. We just chose to do ketone.
Yes.
Okay.
So the aldehyde is straightforward. You're getting a carboxylic acid. The ketone is not, because you have a choice of where the oxygen is going to insert. And so it's basically going to insert into the more substituted alpha carbon. And so in this case, that's going to be alpha prime. So this portion that I've drawn up first is called the acyl portion. The next portion, so the oxygen inserts into there, and that's called the alcohol portion. So an ester is an acyl group and an alcohol group. So if we had to just practice some nomenclature, how would you name that, do you think?
Which one, ketone or the ester?
The ester.
Isopropyl ethanoate.
That would be fine. It's sort of mixing things, but so isopropyl is common. Call it 2-propyl ethanoate. Again, you know, in a multiple choice exam for nomenclature, the right one's going to be there. Just sort of use logic to eliminate why something's wrong. It's usually because of like a count. There's too many carbons or something, or it's not in the right place.
Can we do the wave two, woody reaction?
So, one more thing. So again, that carbon, the reason it's an oxidation, because the carbon's going from 2 to 3 in the oxidation state. So a vitioliphination, you're taking an oxidation state 2, either a ketone or an aldehyde, treating it with an ylide. So an example of that would be, maybe I'll give you that. Give you that, and then sort of think about how you would make the Wittig reagent that would carry out that olefination. So, sort of first questions first. How many carbons are you installing? Just one. So, the way you'd go about making this, so you need one carbon. It has to have a good leaving group. So we'll use methyl bromide. We're going to treat that with triphenylphosphine. So that does an SN2 reaction. So this is a salt. Now you need to make the carbon nucleophilic, so you need to deprotonate it, typically with a strong base. So we could use like sodium hydride. We'll use this solvent THF. So this is making the ylide sodium bromide is the byproduct, and then hydrogen gas is the conjugate acid that's formed. So there's your one carbon unit. So the mechanism would be the following. Again, the big part of this module 2 is you're adding a nucleophile to a carbonyl. So that's like a lot of how the mechanisms start. A carbonyl is electrophilic due to the difference in electronegativity between the two atoms there. So the nucleophile attacks the electrophilic carbon. We break the pi bond. So the oxidation state 2 at this point decreases. The negative charge migrates to oxygen. Phosphorus still has its plus charge. The oxygen comes over to attack that. You get this 4-centered intermediate. So that is now neutral, and it decomposes. Leaving you the alkene plus the byproduct, triphenylphosphine oxide. Next question.
Can you go over, like one example of how like to combine and showing the Amino?
So I guess we'll just do something like this. So this would be a tripeptide. There's 3 amino acids and then 2 peptide bonds. So we have alanine, valine, and phenylalanine. So you'll be given the table of the structures.
So since we're given the table, will you kind of just like take off the side chain and put the nitrogen where the side chain was?
Well, if you're converting this into an actual structure, you have to draw in a specific way. So the leftmost amino acid is the N terminus. The rightmost amino acid is the C terminus. So I guess we'll just go ahead and start drawing this. So we want to draw it such that we get the stereochemistry of the bonds correct. Huh?
All these are S.
Yes.
What is this? Oh, S, sorry, okay, sorry.
So the way I've drawn that, we have to put that stereocenter in as S. So we need to figure out, so alanine, the residue is a methyl group. So we need to, is the methyl group going to be a wedge or a dash? So if we put in a wedge, that center is then S. So again, you want to show some finesse in what you've learned over the past couple semesters about Lewis dot structures. So I want to draw the chain of this basically anti. Like if you look at all the atoms, they're going to be, the stuff that's in the plane, as you'll see, will be anti. So this H is going to go up, then now this carbon is going to go down. So now we have valine, and its side chain is an isopropyl group. So should that carbon coming off there be a wedge or a dash? So what I mean by the chain, the main chain, so see how this, it's sort of, you're looking down a Newman projection, it would be anti, that's what I mean. So we want to make sure that we get these dashes, or these wedges and dashes correct, in that they're all S. So now this one here, the H is going to go down, the carbon goes up. So phenylalanine is basically a CH2 and then a benzene ring. So should that be a wedge or a dash? So I think you can see the trend. If you're drawing it a certain way, if the carbon points up, the side chain has to be a wedge. If it points down, it has to be a dash. So that makes it a little bit easy to remember. So what do you need to be able to do if you were given that structure? Count. If you were given this and not that, how would you know how many amino acids are in there? You can count sort of the alpha carbons of 1, 2, 3, so that's a tripeptide. So then you need to be able to, looking at this, looking at the table, come up with that sequence. So it would be a magnitude of order more difficult if you're not given the table, right? So you're given the table, you just have to know how to use it.
So by using this, can we kind of go over like the problem that we did like yesterday about taking apart, maybe like the hypothesis?
Yeah, I think there's, so I grabbed a different book that has a couple problems. That are different. So just stick with one of these more straightforward ones. So I'm going to write a polypeptide. It's pretty long, and then it's asking you where trypsin and chemotrypsin would cleave it. Sort of ran out of room, but I think that's good enough. So trypsin cleaves basic side chains. Chemotrypsin cleaves aromatic side chains. So just offhand, do you recall what the basic side chains were?
ARG and LIS.
So arginine and lysine. So looking at that polypeptide, if that's treated with trypsin, how many fragments should you get?
30.
So maybe I'll do these and so we're reading it. It will be 1, 2, so 3. So these enzymes cleave to the right of the amino acid. So what maybe does that mean? The ARG or the lyse become the new C terminal in the fragment, if that makes sense. So chemotrypsin cleaves aromatic side chains. So how snappy are you with the responses for that one?
Oh, I thought you meant how many fragments.
So tyrosine,
I promise this is like the easiest part.
It really is. This makes the most sense ever.
Yeah.
phenylalanine, and tryptophan. So how many fragments do you get from that? So one, two. So yeah, 5.
I do fine, yeah. Right.
So it's kind of neat because it's like a detective thing.
So if we have the admin degradation, that is the N-terminus, correct?
Yes.
Okay. And the other one that does the C, what is it, the
Carboxypeptidase.
Okay.
So that's sort of the only one that cleaves to the left of the amino acid.
That's the sick one.
Carboxypeptidase.
So like, you can, is that only for the long polypeptide, or like, can you use that on fragments also?
So what?
The carbox.
So these, if you think about these in the most straightforward fashion, I'm not saying this will happen in real life. I'm just saying, like, if this is like Pac-Man coming to eat this thing from left to right, it's going to give you those fragments. And carboxypeptidase, it's sort of going to read this sequence. Start over there. It's going to clip that off. Then it has a new fragment, and it's going to read that, clip that one.
Okay.
So the carboxypeptidase does not stop. These stop after it hits the coded amino acids. So the carboxypeptidase will basically cleave everything, just starting from that end moving this way.
So, is that like the only type of hydrolysis problem that we would have? Cause like, I know you said you like did some type of mechanism for hydrolysis, and then under it, we did like digestion, which is like, then when we started this, so like. are
Yeah,
you-
so that was to illustrate, like, if you had to make this in the lab, you'd have 1, 2, 3, 4, 5, 6, 7, 8. You have 13 amino acids. I don't even know how many different combinations that could make. It'd be a lot. So, the digestion of that will give you each amino acid. What you could then use a mass spec to figure out what each of those are, but the mass spec is not telling you how they're connected like this.
Okay.
Only sort of this information tells you how they're connected. So if you had to make this in the lab, you have to make it a certain way. So if this is the N-terminus, this N-terminus has to be protected. This carboxyl of that has to be activated. This N-terminal here has to be free to make that bond. So you have to make them in pairs, where the carboxyl group is activated and then the other amine is free. to form the amide bond. So we didn't have time to cover the chemistry of that. So it's not going to be on the exam.
Okay, it's not, so the protection's not, okay, that's what I was gonna ask.
Yeah.
So
What about like the Fischer projections and things?
there may be one. I don't recall.
What is it?
Fischer projections.
Can we go over one of those?
Sure.
Usually it's just on the left of the penultimate, right?
Yes.
I just think L left would be the
Right.
section.
So if we were looking at alanine, so here's the tip, I guess, for an amino acid Fischer projection. The normal S configuration, the amine group is on the left, so that the other term for that is L, like capital L. So this has to be the H, and then the side chain is down, so it's going to be a methyl group. So really what you're looking at for every amino acid they're all going to be that. And then what differs is, so there's a little molecular person. The side chain is isopropyl, which is on the bottom.
So that's all we need to know for that, is that basically that the amine goes to the left, is on the left side.
Okay. And then just look at the side chain to see if it matches up.
Say it again.
Look at the side chain to see if it matches up with like the right amino acid, basically.
Correct.
Okay. While we're on amino acids, can we do like one problem on like the Strecker? What, is that what it's called?
Yeah.
Yeah. Just to make sure like.
Is this gonna be on the test? Did we?
Yeah, this will be on the exam. So this there's a lot of stuff happening in a Strecker amino acid synthesis. You're basically starting with an aldehyde. So the aldehyde has the side chain incorporated, and I'll circle that in red. So that's the side chain. The aldehyde oxidation state 2 carbon condenses with the ammonia to form an imine. So you have a primary amine plus an aldehyde, that gives you an imine. The imine is then susceptible to nucleophilic attack by the cyanide. And that cyanide, that oxidation state 3, that's what gets the acid carbon into the molecule. So the first thing that happens is that condensation. So there's your imine. And then the HCN step gets the oxidation state 3. And then all you're doing at the end here is hydrolyzing that to the acid. So the side chain that's circled in red there is a nonpolar side chain. So you'd go to the table, look up what that is, and that ends up being ILE, or isoleucine. So again, you know, you should be able to see how the carbon backbone maps onto an amino acid. Go to the table and figure out which one it is.
What's like the Fischer Esterification and like how, like is it always that same mechanism that we did in class?
It is.
Okay.
So that's the same Fischer, it's just a different sort of reaction. So I'll just open up a new slide real quick and so a Fischer esterification, you're starting with an acid at oxidation state 3. You have any sort of alcohol and a strong acid, and you're heating it. So it's a condensation where you're losing the elements of H2O. And as the name implies, you're forming an ester. So the oxidation state stays 3. And the mechanism is you're under acidic conditions, so the carbonyl of the acid gets protonated first. Then the alcohol then attacks that, and you have to show positive intermediates throughout the mechanism.
So that can be any alcohol, right? 'Cause I know usually it's like ethyls, ethanol.
Yeah, it can be anything.
Okay.
For the cyanohydrin synthesis, is it always the C end attaching to that sp3 carbon? Like, I guess where, I can't remember, if it's like an O there or something.
So the second step of the Fischer the second step of the Strecker amino acid synthesis is analogous to a cyanohydrin. You're adding the elements of HCN across that pi bond. So hydrin just happens to mean alcohol. So if you were starting with, you know, just a ketone or an aldehyde at oxidation state 2, you have this compound here, HCN, again, pretty standard at this point. The carbonyl gets protonated. The nucleophile then attacks. And then you end up with your cyanohydrin. So that's an example of a nucleophilic addition. So we'll take one more question.
What's the most important thing to say?
Okay, specifically with the bioacetals, we did something with like rain something.
Rain nickel.
Yeah, rainy
Is
nickel.
that always the case with those? Like after we do the SH with the BF3 blah blah blah, like do we always go on to use the rainy nickel?
So again, this is another example of a nucleophilic addition. In this case, you have a dithiol. The Lewis acid is there to promote the reaction. So we're starting at oxidation state 2. You end up with 2, and then with rainy nickel and hydrogen gas. That does a complete reduction to get you down to 0.
One more. If we have an acetyl, if we put water back into it, it'll make it back into the carbonyl, correct?
Can you be a smidge more specific with what you mean?
Like, if we make like an acetal, not an acetyl, like an acetal, and then if you put. 'Cause you
Yeah,
said
so
you put water back
to
in.
shift the equilibrium from the acetal to the carbonyl, you have to add excess water.
Because there was one problem that all it added was H3O plus, and that also changed it back. So can that happen as well?
I'm sure that's what they mean.
Okay.
Yeah, the two are functionally equivalent.
That's for what now?
So she was asking about the reverse process. So how do you unmask an acetal? You have catalytic acid and water. So you get your carbonyl and your diol or your alcohols.
Should we know all the mechanisms for ketones and aldehydes?
Yeah, I would say so.
Just tell me which ones. Okay.
So like, I have another question that doesn't really require you to draw like anything out, but like, so when we were doing amines and enamines, or however you say that, amines were the ones specifically that we had gone over favored the trans form rather than the cis, and like vice versa for enamine. Is it always the case?
The imines favor trans.
Okay.
That's due to sterics. The enamines is, it depends. So that's not probably what you want.